record on this computer. There you go. Right. Okay, so cardiac MR, in terms of applications, have been around since, I would say, the mid-'80s. When I started doing this as a grad student, no, I didn't do cardiac as a grad student. When I first got to Hopkins for like 88, we started doing cardiac MR. And the big deal is, gating to get, when you're acquiring Fourier components as your raw data, the Fourier transform of your object, you hope it's, coherent. So you don't want the object changing and obtaining sort of chunks of the Fourier transform of different objects. You wind up with images that look terrible. So gating is essential, which means you have this ECG leads on the patient. Breath holding is also essential, and we'll see some examples in here of what happens when you don't breath hold. And I'll show you a movie of somebody breathing and just how much, displacement occurs during breathing. It's not really compatible with really high quality MR. One of the interesting things, I don't have slides on this, but one of the interesting things about taking the ECG of a patient while they're in the magnet is that blood itself is essentially a charged fluid. It has an ionic component, so it's basically a charged fluid. And so when you have blood flowing in a large vessel like the aorta, and it's flowing in a very large magnetic field, it's essentially having current in a magnetic field. And what happens when you have current in a magnetic field is by lenses, you get this buildup of voltage across of the aorta, right, as this current flows through it in the magnetic field. And so that voltage really distorts the ECG, right? So it's another pattern. It's a fluid mechanical pattern of voltage that's occurring with the blood flow that gets added on top of the ECG. And it really screws up the ECG a lot of the time. It gets complicated. When I was, in the late 80s and early 90s, a lot of people tried to perform algorithms to subtract away this hemodynamic effect in the ECG. And I'm sure every scanner now has some kind of algorithm that tries to optimize the ECG in the face of this, additional signal. But it was a real problem in that I would say 25% of the patients, if not more, we spent a lot of time trying to get the ECG to be something that we could use. And the way you did that was you moved the leads into different locations such that you maximize the voltage from the underlying, depolarization of the left ventricle. You maximize that and tried to null the hemodynamic effect. And sometimes in some patients it was impossible. So one thing you can do at that point is you can give up and say, I'm not going to use the electrical signal. I'll use a plethysmograph signal and place a plethysmograph on that patient's pinky or on their forefinger. And what happens with that is you get a very broad peak as, the blood flow maxes out in the patient's fingertip. And so we replace an ECG with something that is phase locked to the ECG, but it's broadened. It's much smoother. And so it gives you a little bit more error in terms of when the gating would occur. But in those cases where the ECG was impossible and wouldn't gate, that would come and save you. Another thing you can do is just take data all the time, right? Just continuously take data and then retrospectively go back, partially reconstruct images from short sort of sequences of data. They're not going to be great pictures, but they're pictures that are good enough to tell you where the patient was in their breathing cycle and where the patient is in their cardiac cycle. And so now you can label all of your data as to where it occurred in the cardiac breathing, plane, because you've got on one axis, you've got breathing cycle, on the other axis, you've got the ECG or the R to R intervals. So you can map everybody, all of the echoes you've taken, you can put them in that plane and then just pick a group and make the best picture you can from some segment of that plane.
I had a question about
investigating. Yeah.
When it works, how accurate is it? It's like
that's a great question.
You're trying to freeze the heart within a millimeter of where it was in the last beat.
That's a terrific question. And okay, so the question was, so assume we have a good ECG signal such that we can gate. What is the precision of the triggering based on that signal? Like if the heart, say it's the R to R interval was exactly 1,000 milliseconds for 28 heartbeats. So we have an absolutely reproducible ECG. So that's not a source of error. What's the precision of the trigger given that case? And I would say it's about 10 to 15 milliseconds. It's probably what it is, because it goes on the upswing of the voltage from the QRS. So it's like that R, it's from the R, it's the QRS. So it's between R and S. That transition there is the thing that essentially triggers. And it's somewhere in the 10 to 15 millisecond range. Right? However, a larger source of variability from beat to beat is probably the natural variability in the R to R interval itself. So even if your heart rate is 60 beats per minute, your R to R interval is not 1,000 milliseconds every beat. It's, somewhere between 950 and 1,050 if you're lock solid, right? And so you've got plus or minus 50 milliseconds on the end of things there. So things start to blur towards the end of the R to R interval. You phase lock on the QRS, you can assume that you're kind of on the, at the right point, plus or minus 10 milliseconds. However, the shape of the heart will be slightly different depending on how long the previous R to R interval was. So if my R to R interval, for example, oscillates between 1,000 milliseconds and 750, which can happen, people get in this bigeminy state where they have a short beat, then a long beat, then a short beat, then a long beat. The heart that you measure when the QRS occurs and you're in that 750 millisecond R to R interval, that heart that you're taking a picture of is slightly bigger, right, than the one that you take a picture of in the 1,000 milliseconds, because the 750 milliseconds is shorter, so it fills less, right? And so the heart geometrically is a little smaller. And that'll produce, if you have an alternating artifact like that, you take data at the 750 and then you take data for the 1,000. Those two data sets are interdigitated however you're interdigitating your case-based data. So you might take slabs, each beat, and it will cause an artifact that is dependent on how that mixing occurs, right? And so if you took one line of K-space at 750, and then on the 1,000 millisecond beat, you took another line of K-space, and you just alternated as we go through K-space, that would give you two data sets that were added together, shifted by one position, right? And that's in the Fourier domain. So when you take the inverse Fourier transform to get your image, you actually get two images. You get a ghost image, which is one half the field of view up, and a primary image. And the ghost image comes from that oscillation that you put on your data, right? So that looks pretty interesting because you have this, like, what is that? You've got a primary image and then this ghost image shifted one half of the field of view in the Y direction or in the phase encoding direction. Actually doing, it's a real fun game if you do MRI for long enough, is name that artifact, right? So you look at the picture and it's screwed up in some way, and then you say exactly what happened, to the raw data. And it's a fantastic way to learn the Fourier transform. Because when you look at the picture and there's a ghost and it's reflected, you say, what happened in the Fourier transform, to make that happen, right? And so that it's good practice. Okay. Okay, so just to review, we have a number of ways of obtaining signal from either a spin echo, we went over that. The gradient echo, we'll take a look at what that means. And then these steady state techniques in which you pulse the patient in rapid succession with RF pulses, and it generates this kind of steady state of signal coming out of the patient, and also heats the patient up, right? Because you're putting so much RF in them. So each one of these radio frequency pulses we provide with our transmit coil. And these times between these radio frequency pulses, are on the order of tens of milliseconds between these, if this is sort of a standard old school spin echo pulse sequence. When I started in MR, everybody used these because it was the only way to get a signal big enough to make an image from, because the magnets were of less strength than the 1.5T. When I started, we had a 0.15T magnet, which means that the signal was pretty low. You get this, if there's a lot of decay from a non-uniform magnetic field, this spin echo gives you this nice signal you can make a picture from. And so TE, this time between when you apply the first 90-degree pulse, tip the magnetization into the transverse plane, and you measure your signal, these are sort of on the orders of 10 to 100 milliseconds, somewhere in that space, right? And the height of that in different tissues is proportional to the T2 time constant in those tissues. And that's what generates contrast, T2-based contrast. If we want to do things a lot faster than this, we can go faster by a factor of, say, 10, just by saying, oh, let's forget about all this business. We're going to do an RF pulse. We'll just make our image from here, from this signal. And so as soon as the magnetization hits the transverse plane, starts giving you signal back, we move all of these gradients that are used for imaging and shove them all into this small time space here and make our picture inside here. That means that these gradients have to switch 10 times faster, right? And so that was one of the things that occurred in the technology, was the amplifiers and the gradient design. The self-inductance of the gradient coil was reduced. The amplifiers got a lot bigger so that these ramps could get really short. Ideally, this ramp here would be a vertical line, right? In that I don't want to spend time managing magnetization, pushing it around, and switching my gradient amplitudes such that I can't sample the signal here. I have to wait till it becomes constant to sample the signal. So you'd like to just switch them off. And again, as we said last time, you cannot make this slew rate, or the switching of the gradient, faster than the physiological limit. It's sort of like G-forces in a fighter plane. You got a human in the magnetic or the MRI scanner. If you switch these magnetic fields at a high enough rate, you will stimulate peripheral nerves. And so, and the patient feels it. They're not that comfortable with it. When we first got I think in 1990 maybe, we got the first echoplanar imaging system made by GE, and they had one gradient. No, actually it was two gradients, phase and the readout, were these massive amplifiers that were tuned to a specific frequency, so they could really rock. They could go super fast, right? And so back then you didn't sign consent or anything like that. We just got in the scanner and tried it, and we had, because the phase and readout, we're in the kind of the axial plane. I oriented my body and I moved around in the scanner such that my heart, the long axis of my heart pointed down the z-axis. Okay, so I had the apex of the heart pointing out of the scanner and the base pointing out the other side, but I had to rotate and put my back and my butt up against the side of the scanner, right? And then so we get all that done, like with scout images. I'm getting everything right. And oh, okay, great, let's do it. And so we're going to shoot this echoplanar image, which is when these gradients are like oscillating at ridiculously high rates, so that we get data out very fast. And it makes a high frequency pitch noise, like beep, like when it's doing it.
Did you at least have like earplugs or something?
Oh yeah, you always wear ear protection in MR. There's never a time where you don't. You've got these yellow plugs in there. And so anyway, they go, okay, let's do it. So they hit go, beep, and because my back and my buttocks were right up against the gradient coil, it stimulated a ridiculous response in peripheral nerves and muscle contraction. So I just shot off the wall of that thing, just like a fish in a boat, just like, wow, I just couldn't sit still. It's like, oh my God, that was incredible. So from that time on, that scanner was called the Stimulator. And it was a great scanner. And when you're doing brains with this echoplanar scanner, the nerves and muscles that it would stimulate were on the bridge of your nose. And so when it was pulsing, you could feel like a little twinge of the muscles just on the bridge of your nose, like beep, it would like buzz. And we had, if you change the slew rate by changing, say, this delta t, so it had to get up there faster, you could change it like in microseconds, right? And I went through this, one of my postdocs, who's now a big deal in Turkey, Ergen Adalar, was in the scanner, and he said, oh, I felt stimulation. So I changed the switching rate such that it changed that delta by literally a microsecond. It made it longer. And then I pushed and I said, did you feel it then? He said, no, I didn't feel it. And then I changed it back to a microsecond shorter, and I pushed and he said, oh yeah, I felt it, right? And I said, no, this is crazy. So I made a random list of whether it was on or off, like this microsecond longer, microsecond shorter. And then I just pushed him and said, you tell me if you feel it or not. It was a truly random list. And he hit 100% of them, right? So basically that says that the bridge of his nose was like a 1 megahertz scope. It could tell the difference between a pulse that was 1 microsecond longer, right? Which is kind of interesting. Anyway, side story. Okay, so now we're going to make pictures. The gradient echo pictures are off this signal, and those images can get, or those pictures can get made in like 1, 2, 3, 4, 5 milliseconds, right? This whole thing can be that long. And this is what a gradient echo sequence looks like. When you pull the slice selection gradient is here, right? And now it's here. So you select the slice, you refocus the slice. We won't go into that. And then the signal comes out here. You have a readout that occurs during this gradient echo. Remember, this is all the free induction decay coming down here. So we're reading out here. In order to read out here, we need to pre-phase the magnetization such that it echoes right here. And then we jam in this phase encoding pulse and we step through various values here. So this whole thing can happen like between this pulse and this pulse. This is the signal. Between here to here, it can be really short. It can be down to about a millisecond, right? Now that you have these gradients can switch this fast. So, you know, in 128 milliseconds, you can get 128 rows of data in your K space. So that's pretty good, right? We're talking almost 10 frames a second at this point, right? The problem with it is this signal is not that big. It gets, as time goes on, as you pulse with more and more RF, it decreases. And so you're working with a very small percentage of your total signal. And so the images, you can make MR images at, you know, 20 frames a second, but what you make is 20 crappy images a second, right? Because the signal really gets down low. So this basically gives you some instinct as to how this works out. And that is, if I do an RF pulse here by T1, if after this pulse, there is no MZ or no magnetization left, I take it all, put it in the transverse plane. Remember, the T1 recovery curve looks like this. This time to get all the way back to here is on the order of seconds, right? So that's, these two RF pulses have to be seconds apart, or 5. And then if you bring them closer together, what happens is when you apply the next pulse, which happens sooner, happens here, the magnetization hasn't recovered entirely. And so you bring it back down to the transverse plane and you image with whatever you have there, right? And then do that again, image with whatever you have there. And you can imagine as these pulses get closer and closer together, you get farther and farther along this thing till finally you're just imaging with a tiny little bit of magnetization, right? The other way of doing it, though, is if you organize the phase shift of the pulses correctly, you can get this kind of steady state of RF pulses and echoes occurring in a continuous way. And these are, it's called steady state free precession. And you can image it anytime in here, right? So you can image with this stuff where it's decaying, you can image in this stuff where it's coming back. And then you usually don't image when you have an RF pulse on because you don't want your receiver electronics on when you're pulsing with your transmitter because it's many orders of magnitude higher than the signal that you receive. So normally you just would do something with the magnetization that's occurring here to make a picture, right? And that's steady state free precession. And most cardiac now is done with that type of imaging. In terms of what MRI is amazing at, there's two things in particular in cardiac MRI that are amazing compared to everything else. One is perfusion estimate, and the other is what's called late enhancement or infarct detection. So here's a stress CT image and a rest CT image. Stress usually means in this context the same as nuclear medicine stress. We give the patient some drug that increases the demand, the blood flow demand. And that drug could be dipyridamole, adenosine, something like that, that just opens up the vessels. And so at rest, you see a signal intensity that looks like this. And at stress, you can see, slightly perceive, there might be some dark spots here. Stress CT, it's not great. Like I have to tell you, we've done, theoretically it works. Practically, these signals, as we saw the other day in the physics talks, are kind of on the order of the natural artifacts in cardiac imaging and CT. And so these differences are really small, unfortunately. We'd be great if they were big, because look at the resolution, right? You could get everything. But in MR, you get the signal response that looks something like this. And in the rest case, this patient has sort of normal flow compared to the rest of the heart. In the stress case, when the blood flow in the myocardium has gone up by, say, a factor of 4 in the normal tissue, it just can't make it in the tissue that has some problem upstream. So it's usually a stenotic vessel upstream will not allow the flow to increase past a certain limit. And therefore you've successfully detected a myocardial perfusion deficit. So that person's positive. They have a positive perfusion scan. Remember, in nuclear medicine, this donut, would be really blurry, but you would hope that you would see sort of a darker signal down here. And to be honest, for this patient, you don't really need high resolution here. We just need to detect that's down like on half the dang heart, right? Yeah. So resolution isn't a key element for that patient, right? You go back to the CT and say, well, look at all the coronaries. This person's coronaries obviously have been under a transformative process because they have all of this calcium lining the vessel. Again, to review, this makes reading coronary artery angiography with CT, very difficult, you know, when you have that junk, you know, all this calcium stuff sitting in the vessel. You can't really tell if the vessel's open or not. So here's an interesting paper, this one from, you know, it's fairly recent in my mind, not in your mind probably, where they took 3 Tesla MRI and did fractional flow reserve in those patients. And remember what fractional flow reserve was. You take a catheter and you put it in that vessel. You measure pressure distal to a lesion. You measure pressure proximal to a lesion during some kind of demand like adenosine injection. And then if the pressure drops by more than 20%, you say that patient is abnormal. That lesion is significant. So this group is one of the best groups in the world on cardiac MR, actually. Did those FFR measurements and did myocardial perfusion with MRI. And so this is the reduction basically in that brightness, you know, on the perfusion scan. And so for those patients who had a normal FFR, you can see there's a distribution of increased brightness during stress, and in those below, there's this distribution of decrease. So, you know, looking at this data though, there's a couple of questions when I look at data like this. One is like, why does each distribution here not follow its own normal distribution, right? So if I look at the distribution of these points, it looks like a normal distribution that's been cut in the middle, right? In biology, usually what happens is when you make some kind of criteria like this, you usually get a normal distribution in this direction, right? And same with here. It looks like this has just been magically cut off. So I don't really know. I think there's some kind of selection bias maybe going on in this data, because it doesn't look like natural data to me. Now, what does look natural though, is if you combine both of them, you get what looks like to me a normal distribution, right? You got a big dense center and it gets dimmer as we go, or less to the sides. So I don't know. I haven't talked to them about this data and why this is a magic line. It just stops being a normal distribution at that line. But forgetting about that secondary point or second order effect, definitely there's more points down here when the FFR is abnormal. Okay. And it's not surprising, just from practical experience at looking at a lot of MRI perfusion scans. And when I was at the NIH, there was a team there that were just pushing this technology as hard as they could. And it was absolutely clear that MR is just the best way to do perfusion. The next thing we're going to look at is this effect in MR where you get this late gadolinium enhancement or a real brightness in some tissues in the heart. And those tissues that have this real brightness on T1 based imaging are normally infarcts. So they're tissues that are dead, essentially. They can still have flow, like the contrast gets into those tissues through some vascular access, but it sticks around for a long time, right? It's kind of, so you have brightness. So this is the concentration of gadolinium. And when if you take a set of tubes and you put increasing concentration of gadolinium in this set of tubes, you start with water, and then get progressively higher concentrations, and you perform a T1 weighted image, those tubes that have the high concentrations of gadolinium have very short T1s, and they show up really bright, usually on T1 weighted images, and the water shows up really dark. So you can see as the concentration goes into the blood pool, the signal becomes very high on MR. And then as it's washing out and getting filtered out by the kidneys, it decays away. And this, the loss of this signal is truly the stuff getting shunted out of the kidneys and accumulating in the bladder. If you image the bladder, you would see it gets brighter over time like this. Normal myocardium, we see an increase in signal and then a decay away as it washes out of the myocardium. In an infarct, the increase is slightly slower, but this is the big deal, is it just doesn't wash out. It stays there for many minutes. And so oftentimes you image these patients, anywhere from 10 to 15 minutes after you inject the contrast to look for the late enhancement, which presents you with either a limitation or an opportunity, right? The limitation is we got to hang around for 15 minutes. This scanner is costing us $800 an hour, right, to run, and I got to sit here for 15 minutes. Okay. The opportunity is, oh, look, I got 15 minutes. I can do a whole bunch of imaging of this patient in that 15 minutes, but it has to be something compatible with having just injected contrast. So here you would do the perfusion part, right? With that injection, you may as well do a perfusion exam because you have a dynamic injection. When you have this, you have a dynamic process in the sense that the brightness of the blood is decreasing over time, etc. However, you can still make some really nice pictures, right, during here. So normally you would try and do something with this time, like make movies of cardiac function is one thing. Another possibility is to make flow images. So as we'll see later, with MR, you can estimate the flow for each voxel. You get a vector actually saying what the flow is over time. We could do that, okay? And then you go back and do this image at 15 minutes to get whether or not there's infarct in that heart. We looked at this graph, I think last Wednesday, where we have normal myocardium and this is time in milliseconds. So this is about 2 seconds from here to here, say. Remember this, look, these are minutes along here. This is minutes, right? This is seconds, and this is the magnetization recovering. And in the infarct, once it's loaded up with this contrast, so it's in this condition here, right? So it's got a lot of contrast still in it. And the myocardium the contrast has washed out. Okay, so the T1 goes back down and the myocardium gets darker on a T1 based image. And so here's the scar with shorter T1, and we're going to have a signal difference here. So we can perform some kind of MRI pulse. This could be a 90. In this case, they say, well, let's do 180 degrees. I'll take my magnetization, take it from M naught and take it all the way to minus M naught and generate contrast between these two curves as they recover. And then at some delay after this, I'll make an image right here. When I say I make an image on a time scale, it can be sort of like this box right here, right? So it's like, boop, I'm going to make an image while this is here and this one's here. So this should look brighter, right? The signal's bigger. This, if you wait to the perfect time, you hit a null point, and you will get no signal from the myocardium. So you get 0 signal. It's kind of a special point, but if you're willing to reconstruct images that have negative signal, it doesn't really matter. This distance here is the contrast. Right? However, people spent years figuring out how to find this null point efficiently. For some reason, a lot of manufacturers don't want to make phase sensitive images. So that means they don't want to have to make negative pixel values. And the reason is a lot of things in MR change this global phase. And so when you try and make a picture that has both positive and negative pixel values, those positive and negative values can get affected by other things like magnetic field inhomogeneity, motion, stuff like that. And so it complicates the reconstruction. These pictures are pictures of the magnitude of the magnetization. They don't have any phase information in them at all. There's 0 to whatever the maximum value is. And when you do that, you get pictures that look like this. If you make an image here right after the 180-degree pulse. So if we look down here and say, look, this is already positive, this is negative, right? But when I reconstruct it, I plot the magnitude of that signal, and so it looks like a positive number. But truly, the myocardium here is negative, and you can see what happens when I go from the myocardium into the blood pool. This is negative. This is indeed positive. When I cross over, there is a point, the partial volume, where I have equal, negative myocardium, equal positive blood. They combine to give me 0. And so you get this interesting, it's an image effect, right? You could call it an artifact, but it's an effect, right? So you see this boundary really well. If we wait, out until the myocardium itself is around 0, we'll see something that looks like this, where the myocardium is nulled and the infarct itself, because it's recovered to a positive signal, is bright. Go out farther, the contrast between the two can change a bit. And if we go out even farther, the contrast starts to go away, because the recovery now has made both of those magnetization vectors come to the same value. So any one of these two is probably just fine to use. And so you just want it to be somewhere around here if you're going to do this magnitude reconstruction. So again, I think this is the difference between magnitude reconstruction and phase, in the sense that you can have negative values for your myocardium, positive values for your infarct, and you get a much higher contrast between these two than here. Okay. You can achieve very high resolution pictures. Well, high resolution in the sense of MR high resolution pictures with a delayed enhancement, and it gives you some information you don't get from, let's say, CT. Even if you had a really good stress CT exam. So here's the rest, here's the stress. You have this kind of dark signal here. It's not hugely dark, right? And we saw, again, if we recall, how big the artifacts are from, say, the shadow that's cast by this contrast in CT, right? So we've got, as the X-rays are coming through, you get beam hardening, all this stuff happening, changing the signal value around it. But we'll say this is a positive stress CT. What you don't appreciate in this CT is that this chunk of tissue right here, which is all along here, is dead. There's an infarct, and it's a really narrow and thin infarct right there, right? This is saying I've got low perfusion, but it's not dead, which is good. That means if we, intervene and open up that vessel, the tissue downstream is viable. It'll probably just recover to normal function. It's not dead yet. I'm not dead yet. So this patient has this thin film of infarcted tissue just on their endocardium, which to me is kind of strange, because you would imagine that all of this blood right here is highly oxygenated. So like, why is it not sort of at least diffusing into the myocardium? But it probably is at some level. Maybe this really dark rim here is still viable tissue, right? So this is what, on clinical MRI with the clinical resolution, and it's 1.5 by 1.5 by 8 millimeter square voxels. And this is a heart. This is myocardium that's normal, and this is myocardium that's infarcted and has this enhancement, this late gadolinium enhancement. And what was for years in the literature, people talked about a gray zone, which is this sort of gray signal here, this mid-gray signal here, being some kind of special, case of tissue and whether or not it was predictive to have this gray zone. But when we went in, we took these hearts, injected the contrast, and sacrificed the animal, and said, well, let's make a high resolution of this gray zone and see what it looks like, right? So we did that, and that's what it looks like, right? So it's not gray zone. There is only infarcted tissue and live tissue, and this basically is just partial voluming at the clinical resolution, okay? And so if we, zoom into that part and just look at that tissue. So here we are with this, purported gray zone, and we take a look at what that actually looks like when you image that thing for 2 hours. That's what it is, right?
So, I mean, at least when I've heard about infarction, I've heard about like the penumbra, like the tissue that's at risk.
Right.
So is this saying that like the penumbra is not like
it's not simple
there? Or?
No, it's just not simple. And so the question was, the concept of penumbra around a lesion is the tissue that is most susceptible to misbehaving such that it kills you, right? So the penumbra, it would seem that if you get a fatal arrhythmia that originates from some tissue around an infarct or a lesion, and that's the way many people die, right? A fatal arrhythmia is generated by arrhythmogenic tissue next to this infarct. What is it about this penumbra? Is there something that we can say with MRI, that will tell us it's more risky or not? And this image would say, well, the penumbra is not actually some different type of tissue. It is a mixture of normal, viable tissue, maybe not normal, but viable tissue that is not infarcted, with interdigitated infarcted tissue at really high detail and high frequency, right? So when I look at this and say, look at these tiny little strands of infarct that is infusing this quote unquote normal tissue or non-infarcted tissue. And here I have a strand of non-infarcted tissue here. Here I've got strands of non-infarcted tissue, and they're all sort of mixed together. This actually looks pretty dangerous. And the reason is that if you stimulate tissue electrically in order to make it depolarize, so these are myocytes that depolarize, right? How they depolarize really matters on what bath they are in, right? So if I'm a myocyte and I look around and say, what am I connected to? I'm connected to normal myocytes, then you just have this normal sequence of activation. However, with all the myocytes along the edge of this thing connected to infarcted tissue, the whole field effects and everything are going to be different. And so what happens is the transmission of the electrical depolarization of the tissue through chunks like this looks quite different than just when it's, going through normal tissue. And so that can cause actually the wave of depolarization to slow down, right? And when it slows down, when it emerges, so let's say in 3D, the depolarization is coming through this point, and it depolarizes and comes back around here and then goes underneath this thing and comes out here, and then it can reconnect with this at some place a 5 millimeters away after that tissue, right, has repolarized. And then boom, you've got a circuit, and that circuit just continues on its own, because it's like a cat chasing its tail, right? When it basically, the depolarization wave comes around in a loop, and when it gets back to the beginning of the loop, that tissue has already repolarized and it fires it again. And it just maintains that circular, sort of excitation. And so what we did with this was we imaged a lot of these infarcts, and then we quantified tissue with it's channelness. Like, what are the channels of normal tissue that are running through this? Is there a way mathematically to say, you know what, this tissue has real high channel number, and therefore it's going to be risky to for generating arrhythmias. And you can do that. We did this in a bunch of infarcts, right? And look at all of the details. So these are all hearts in jars. You can't do this in a living heart. And this comes back to your original question, which was like, what is the precision of triggering, when you're triggering off an EKG? And what's the precision of imaging, basically? When you're trying to trigger off an ECG, you're trying to make the patient hold their breath, and the heart should be coming back to the same place every beat. So to make images that look like this in a beating human heart was a goal of ours about 20 years ago. We said, okay, I can let the patient be in there for 20 minutes, 30 minutes, an hour. Let's see what happens if we image them for an hour and just get more and more signal, such that we can make smaller and smaller voxels. I went through 2 PhD students and a postdoc and myself and 1 junior faculty. We did this for 2 years, probably. There was a certain blurriness past which you could not get, right? It just, regardless of how well you thought you were measuring local motions and correcting for that, when you put all of the data together to get voxels on this size, it just came out blurry, right? And so we just gave up after a couple of years and said, look, the reason this is happening is because it's like a fundamental uncertainty principle of hearts. It doesn't come back to the same place.
Yeah.
Right? That's the problem, is that if you waited for it to come back to the same place on this spatial scale, you would be waiting orders of magnitude longer than you have to make the image, right? Because they just don't come back to the same place. And in fact, they probably distort in some way that is highly difficult to correct, view to view. So unfortunate that, I thought we were going to get pictures that look like this in humans. And then the idea was, okay, I've got this picture of your heart. I can tell you beyond a shadow of a doubt if you need a defibrillator or not. Because given the patterns that I'm seeing here, you have a 50% chance of going into a fatal arrhythmia in the next 2 years, right? That kind of thing, right? And that cannot be achieved, like the imaging cannot be achieved, but that goal, it seems, will be achieved just by using the blurrier pictures and simpler electrical modeling. It looks like there will be some good advice given to patients as to whether or not they need a defibrillator. And most of this work is now done. Farhad was a postdoc. Where's Natalia's name? I guess we'll see some of her data later. Natalia Troyanova at Hopkins, and she had this massive racks of supercomputers doing electrical depolarization simulations based on these data, right? So we would feed this data into her simulations, and she would see what was arrhythmogenic. And so now you can get reasonable images of humans, take a look at it, and make a reasonable, with the system she built up from these simulations, a reasonable guess as to whether or not this person's at high risk for a fatal arrhythmia. It's pretty cool stuff, actually. I really like that project. The other thing that when you're looking at these late gadolinium enhancement images, this is a high resolution picture of late gadolinium. You try and do it higher and higher with people, and it just doesn't get that much higher than this. But you can see sort of details here, right? There's this endocardial thing that's not enhancing. There's stuff in the septum here that basically isn't enhancing. These dark bands in here are usually regions in which the blood doesn't even get to, right? So it's like you've plugged up all of the small vessels with hemorrhagic sort of clotted blood, right? And so when you see this on a late gadolinium enhancement, and you can see that there's a real dark band there, usually the tissue is still at its original geometric width, but there's a chunk of it that just isn't getting blood flow. It's just filled with crap. And then this stuff is getting blood flow, but it's enhanced, and so it's highly likely it's infarcted. And then if you come back to this patient 4 months later, you can see, oh, okay, well, all of this stuff was actually getting no blood flow. It is all now infarcted neatly. This stuff probably still isn't getting blood flow, right? So very detailed pictures of the state of being of a patient's heart post heart attack. So the friends that I have that have had heart attacks, right? You know, you ask them, oh, do you want to get a picture? You know, gadolinium picture and see how you're doing? Each one of them said, nah, it's okay. So it's an interesting question, right? Like, say you did have a heart attack, you know, and you go to the ER, you have an EKG abnormalities, they take you to the cath lab, put a stent in, your EKG resolves, and you seem okay. Okay. Would you go get an MR and see if you have a big old infarct in there?
I would, because I'm curious.
So yeah, I would too. Because I would want to know, should I really start thinking about a defibrillator, or should I like have a bracelet that says, dude, I've got a huge infarct. If I fall on the ground, don't wait, take me to the cath lab. Don't work me up, just get me in there, right? And but you know, a lot of people, if you wake up every morning and you have that picture in your head, you go, oh, geez, you know, I got this thing. It's like having a car that has a dent on the fender. You know, you've got this beautiful new car, and you're like, the only thing you can see is the dent, you know, so. Okay, so let's go back to these T2 weighted images. And like, remember, most of our scanning in the heart, we're going to do with this stuff, this FID, so that we can get it done really fast. Now the question is it useful to know what the T2 decay of the tissue is? And in the last decade, fundamental imaging or imaging of the fundamental parameters T1 and T2 have really come into their own. When I first started MR in the late 80s, you know, we did this. We made T1 pictures and spin echo pictures. And my PhD thesis was on it was actually machine learning using these features to optimize what kind of pulse sequence you should use to answer specific questions. Unfortunately, I didn't call it machine learning. I called it statistical decision analysis. That's what it was called back then. And so, you know, it lives in obscurity because machine learning back then wasn't a thing. But so the question is, like, if you really know what T2 is and you really know what T1 is, can you make any statements about the underlying health of the tissue? Just to review, remember, T1 is the recovery of the magnetization after, say, a 90-degree RF pulse in this case. And, you know, it's on the order of 500 milliseconds in the heart. T2 is basically this recovery here after 180. You know, the whole FID, the true T2 decay is given, okay? And these are like 10 times shorter, 15 milliseconds. So here's images when you take a spin echo of a patient who's had some kind of heart attack or is in chest pain and stuff like that. Well, this is an acute infarct by the look of it. But anyway, and you image the T2 as a function of position in that tissue, you get this really bright spot. That means the T2 got really long, right? When it got really long, what's that mean? It means the tissue is swelling up. So if you injure tissue, let's say you burn tissue, right? You know what happens when you like touch the stove and you take your hand away, and then 10 minutes later, it's all swollen up, right? So it basically, this is swelling up of the tissue after an acute injury, right? And you get this T2 weighted increase. So all of this tissue has undergone an insult and is injured. And you know that because of this T2, and you know that right away. When you look at the late gadolinium enhancement of that tissue, it just doesn't enhance. So it's not dead, right? These cells are still, they're still fighting. They're still going for it. If you look much later, right, and you look at the T2 weighted image, things have evolved. And now we have a bright rim all around this segment of tissue here that is also highlighted on the late gadolinium enhancement. So that those cells are in tough shape, right? They basically are not coming back. And you have this dark rim inside here, which is likely tissue that just isn't getting any blood flow. It's filled with myocardial hemorrhage, right? Or just so an unfortunate sequence of events there, right? But acutely, this tells you, oh man, this is, the injury is here. Acutely, this doesn't tell you much, the late gadolinium enhancement, right? So T2 weighted imaging, early gadolinium, and then late gadolinium, okay? Early gadolinium, you can see here there is a deficit where the blood flow just isn't getting to. That deficit is pretty clean right here. And in the tissue where the blood is going, where we have late gadolinium enhancement. Okay. So let's look, we're going 15 minutes. Okay, this is a totally cool part of MRI. If you really want to know more about MRI imaging, I would pick this as something to really spend some time on, because it's great. And what happens is, remember we talked about positive and negative signals and reconstructing phase angles. This uses the phase of the magnetization vector to determine if it's moving while you're imaging. Okay, so the magnitude of the magnetization vector, let me see if I don't have a picture. Let me go back. How do I end this? Do I have a picture? Huh. 16. Let's see. No. Oh, wait, I have one in here. Huh. I don't. Can't believe we don't have a picture of the transverse plane. Sorry for the delay. It'll be worth it. Okay, here we go. Okay. This goes back 2 lectures. And here's our magnetization vector. When we tip that magnetization vector with an RF pulse, say a 90-degree RF pulse, the magnetization vector goes into the transverse plane. There is no M naught left here. Remember, it recovers with T1. This vector that's in the transverse plane decays away with T2. It has, its phase is equivalent to its position in the transverse plane, okay? And what you can do is, when you make an image, you can not only give the length of this vector in your image, you can tell what the phase in the transverse plane is of that vector, okay? And let's see, that's T1. Okay. So that phase angle, so here you can see magnetization comes down because of magnetic field inhomogeneities. The different voxels process in the transverse plane at slightly different frequencies, and so they get dephased. This phase angle is measurable. When I take an image of a voxel, I know its magnitude, which is the length of the vector, and I can tell you its phase, right? We can control that phase. We control that phase with the gradients, right? And here, if I put on a gradient, let's say we're in the X direction here. And so I turn on a gradient, so a negative X gradient, and then I turn on a gradient that's in a positive direction in the X direction. It's called a bipolar gradient. If I look at a stationary spin at a specific displacement, if this is an X gradient, a displacement in the X direction, its phase will change according to the amplitude of this gradient in a linear way over time. And then when I do the opposite gradient for the same amount of time, that phase will evolve into the opposite direction and come back to zero. So I've basically refocused it. The interesting phenomenon is when that voxel is moving. So let's say it's a voxel that contains blood and will track something that's 1 by 1 by 8 in the blood, and will track that blood. When it's moving along the gradient direction, the phase in that voxel doesn't go linearly anymore. It actually goes as a quadratic with time, right? And when we switch the orientation of the gradient, the phase evolution still goes quadratic with time, but it doesn't refocus at this time. Because it's quadratic, there's a net phase difference here, right? So it doesn't come back to zero. It actually goes past zero and keeps going. This net phase difference here is linearly proportional to the velocity. So that if you can measure phi, delta phi, there you have a number which is linearly proportional to the velocity. So if we just make a picture of those numbers, it's a velocity picture, right? And so here, this image is a raw image of phase angle. So a magnitude image looks like this. In fact, these aren't the same slice. I think this line here shows this slice. So look at the air. So this is air back here, and this white noise up top here is air. So the phase angle from the magnetization vector in the air is random, because the X and the Y component are just noise, and so you just get totally random phase angles. And so that's what that looks like. This is stationary tissue, and the phase angle, let's call it 0 degrees, is 0 degrees in the stationary tissue. And so it looks like this gray value here. And the phase angle in this and say this changes over time. And the reason is the velocity of the blood coming through the plane is changing, right, over time. And so I'm building up phase angles as my velocity goes up. And if my velocity is in the negative direction, I get phase angles that are in the negative direction, right? And so it's totally cool, right? In that we just make a phase image and you get a flow image. And some of the things that get in the way are the fact that if you just plotted one simple raw phase image, this actually is a difference image between a baseline and an encoding. If all you do is plot the one image here, you would see a lot of phase shifts across the background. And those phase shifts are caused by differences in the magnetic field strength, et cetera, et cetera. So you have to subtract away those baseline phase shifts and look at what's left just from the gradient switching. And that gives you this flow picture. If I put, a region of interest right here in image J or whatever, and I plot it, it looks something like this. I can convert the flow to milliliters per second by converting my pixel values to, meters per second or centimeters per second or whatever, and then integrating over, say, the aorta, and I get a flow rate, per unit time. And so, or you just, so it's ejecting blood here, and then you get retrograde flow. The flow's going back in the negative direction, right? We can look at asymmetries in the flow. So if I take my scout image and then I say, I'll pick a plane perfectly perpendicular to the aortic root here and plot it, then you can get these detailed maps of what the flow pattern is over that scale. Here, this is the descending aorta, which is a very nice sort of uniform flow coming down towards us, or actually, yeah, I guess towards us. This is ejecting, so dark would mean a phase angle that is flow going away from us, and then this would be flow going towards us. You can also see in the background, so this is all zero. Say it's not, there's no flow here, so it's basically zero, but above your data right here, you can see all of this noise here. That noise is essentially from the inconsistency from beat to beat of this flow data. And it causes, those inconsistencies are things that as you're encoding from one phase encode pulse to the next, you have just a noise term, which is an inconsistency. And that shows up as basically a noise stripe in the phase encoding direction. Right? So it looks like this is a little bit more noisy than this because there isn't really much of a noise stripe here. This just reproduces itself every beat. And the heart is pretty good at reproducing flows, remarkably good, actually. So you can look at the cine MRIs, and you can get immediate appreciation of some flow that isn't happening, right? If you had flow that was or stasis in, say, the apex of the RV, you can see that right away. So you can compute all of these things that are computed with echocardiography in terms of flow rates through different vessels, etc. You can also compute them. Echocardiography has limitations when it's using Doppler, and we saw this on one of the problem sets, is that if you can't get a really good angle, your estimate of flow using Doppler is going to be noisy, right? Because the flow isn't towards the transducer. Whereas in MRI, you basically can get flow in any direction you want. You just select that plane and maybe do your flow encoding perpendicular to that plane. And you can use flow encoding or velocity imaging to actually image the velocity of the myocardium, for that matter. So as you're watching the heart contract, you can measure its velocity of the muscle and make a picture of that as cardiac function. That's not done that much anymore because most of the time they just look at cines and do feature tracking to get velocities of solid objects like the myocardium. This is a technology that was developed by Albert. Well, it's developed by a whole bunch of people, but Albert is one of the world experts on it. And when he was at Stanford, he did this, and then he's been doing it here a lot, which is, it's called 4D flow with MR, and exactly as it sounds, you image a 3D vector field that represents the flow direction of the blood, and you make those fields, or you measure them at different parts of the heart cycle. And you get these amazing evolving vector fields that tell you about flow function in the heart. He does this in 4D in the sense that puts the patient in the scanner for a long time. They sit there, they breathe, correct for the breathing, And you know, it takes 20 minutes to get one of these because it's you got many slices, you got a lot of vectors to encode, etc. But it gives you some very interesting stuff. Like here, you know, this is a regurg through this valve here. You can see as a jet in this flow field. What was this? Oh, this is regurg in the pulmonary valve there. And, you know, when you have the 4D data, you can retrospectively go back and just put a plane anywhere and decide where is the, you know, the critical flow fields that I need to measure in this patient. And sometimes that's important because, for example, these patients in tetralogy below, they're no two are exactly the same. And when you're trying to plan surgery and everything like that, you'd like something that is really customized to that patient. So here's an example of flow out of the aorta, and then there's a chunk of regurgitant flow here that you can measure quite accurately. And so the net ejection out of the left ventricle, you know, is basically this curve minus this one. So it's the ventricle has to beat a lot more, beat a lot harder to make that happen. Okay, so I'm going to stop there. And I will, as I said before, I'll post the sign up for when you want to give your project presentation. I'll post the video for MRI. Are there any questions from folks online? You can just speak up if you got a question.
You also put up the homeworks 5 and 6.
Oh, homework 5 and 6. Yeah, I can put those up too. Let's do, yeah. One of them I decided what probably we weren't going to do, but I'll put the other one up. Okay. Yeah. They're up. Are they not up?
Yeah, they're up. There's just no like submission.
Yeah. So I'll put the submission date on it, and also the answer key, which is good to use. Okay. Everybody good? All right. We'll see you on Monday. And if anybody signs up for Monday, we'll have at least one presentation Monday, or whoever wants to get it done Monday. And then we'll do some more MRI applications as well.